Hello everyone, and welcome back to this tutorial series on the theory of computation. In this video, we'll be introducing the notion of NFAs, or non-deterministic finite automata. So that's going to be the very first topic of this set of slides. We're also going to be discussing the relationship between NFAs and DFAs. Okay, so let's jump right into what NFAs actually are. And to do this, I'm going to start by giving you some high-level intuition. Okay, so far, most or all of the machines actually that we've seen were DFAs. Okay, and so you remember that DFAs, or deterministic finite automata, right? The D here stands for deterministic, is a 5-tuple, right? Which we wrote M is equal to Q sigma delta Q0 F, right? So it's a set of states with a given alphabet, a transition function, an initial state, and a set of final states, okay? And we saw how a DFA can be seen as a computational machine in the sense that if you have a DFA, right, so you have a DFA, and you give it some string W, you can think of W as being on some input tape, right? So just think of this very long tape on which you put symbols at given spaces, right? So if you give this input tape to your DFA begins its computation at the initial state. And to do that, it starts by reading the very first letter of the string W. And so by very first, we mean the leftmost letter, of course, right? And so it uses its transition function, delta, to go through each of the letters in the string W. And as it reads the strings in the letter W, it transitions to the states that are specified in its transition function, right? So for instance, you can imagine if the very first letter on my input tape was A, and of course I started at the start state Q0 and I read an A, perhaps my transition function would tell me to go to Q1, right? So formally that would look like delta Q0 reading an A goes to Q1. Okay, that's how we wrote it for a DFA. Okay, and the reason why we called DFAs deterministic is because given a state and a letter being read, the machine would go to exactly one state. Okay, meaning that for any state and for any letter that your machine was reading, the next state that it would go to was deterministic, right? There wasn't a choice to be made, okay? So the key here is that there was no choosing the next state, okay? And so that means that from start to finish, if you were to give your DFA M an input string W, right, from start to finish, it would start at Q0, it would read through a series of transitions, the string W, and it would finish at some state P, okay? And then we said that W was accepted if and only if the state that would be reached while reading W from Q0 belonged to the set of final states of the DFA, right? So the set of final states, which are also called sometimes the set of accept states. And that's actually arguably a more appropriate name because what it means for a state to be in F, in the set of final states or the set of accept states, it means that if a string can reach it from Q0, then that string gets accepted by the machine. Okay, so that was a recap of DFAs. Now, what does an NFA add to all this, right? Well, an NFA introduces the ability of making a choice. So an NFA, where the N stands for non-deterministic finite automata, this non-deterministic term, what it means is that your NFA now has the ability to make a choice. It might not always have to make a choice or have the availability of making a choice, but now your machine can work even with the possibility of being able to choose, okay? And so what do we actually mean by choice? Like, there doesn't seem to be something that you can choose from a bag here. And so what do we mean by choice? Do we mean by choice? Well, this is directly related to the transition function, okay? And so in a non-deterministic finite automata, it is allowed for a machine to choose between, say, two states when it's at one particular state and reading a given symbol. So, for example, it's possible that in an NFA, so imagine this is an NFA, it's going to again have an initial state, but now what could happen is it could be reading the very first letter of the input symbol and have a choice to make. So Q0, while reading an A, NFA could either transition to, say, Q1, or it could transition to Q2, right? So automatically here, you create a choice. So a choice is created, okay? Meaning that now your NFA has to choose when it reads this A, does it either go to Q1 or does it go to Q2? Okay, that's what we mean by making a choice. Okay, and this is illustrated, in fact, in the formal definition of the NFA, which we'll see in a second, by the fact that now, when you're reading a symbol, so A, and you're in some state, say Q0, your transition function now returns a set. Okay, so now this is very important. It returns a set of states, and this set of states represents the choices that you have. So here, this would be when you're reading an A at Q0, you can either go to Q1 or Q2. That's what this is saying, right? So here, this is saying the NFA can choose between going to Q1 or going to Q2, okay? So this is very different from a DFA, because in a DFA, when you were reading a symbol at a particular state, you always returned a single state. But now what you return is a set of states, okay? And what happens now when an NFA has to accept a string, okay, what it does is it's going to try all the possible choices for each of the possible states when it reads a whole string W, okay? And if in any of those possible walks that it can choose from, you reach a final state, then your NFA accepts the string. So you can imagine this as, instead of this picture where you only had a single walk, you can imagine, and this was for a DFA, you can imagine for an NFA, if you're reading a string W that started at Q0, your NFA would try all the possible walks. So maybe this is walk 1, reading W, right? Of course, you always read the same string W. This is walk 2, reading W again, and so on. And so perhaps this first walk goes to a state P, this second walk goes to a state M. It's fine if P is not in F and M is in F, right? As long as one state, at least one state, that can be reached from one of the walks that the NFA can choose from is a final state or an accept state, the string gets accepted. If no walk leads to an accept state, at that point, the NFA rejects, right? So this would lead to an accept, to the NFA accepting. Okay, now this has been very abstract so far. Let's actually look at a formal definition. So again, a non-deterministic finite automata is, like a DFA, a 5-element tuple, which is going to look very familiar, right? So it includes a set of states, an alphabet, a transition function, an initial state, and a set of final states, okay? The only thing that's different from a DFA is how the transition function looks like and how it works, okay? So you'll notice here that the transition function, now what it says is that it can accept a state. So that's similar to the DFA transition function. I'll just remind you that the formal definition of the DFA transition function was something like this, right? So it took a state and a symbol and it returned a state, okay? Now what this is saying is that the transition function so let's say this is for a DFA and this is for an NFA. The transition function for an NFA, again, takes a state, but now it can either take a symbol or, we haven't discussed this yet, it can also read lambda, okay? So this is reading the empty string. And we'll discuss what this means in a few seconds, okay? But this also provides the NFA with some nice additional, with a nice additional tool that's very convenient, okay? And so what this is saying is that you take a state and either a symbol or lambda, and you return. Now this is the power set of Q, okay? So that means that the return type of delta NFA is now a set, okay? The return type is a set, meaning that your transition function returns a set of states, okay? And so what's interesting is that the set of states could also be empty, right? So this includes the empty set. And so what that would look like a transition where you have perhaps some state Q4. It has the transition for A, but it doesn't have the transition for B. And so if you're at Q4 and you're reading a B, your NFA jams and it gets stuck at Q4. Okay? Okay, so now that we've talked about the formal definition of an NFA, what does an NFA actually do? So, like a DFA, an NFA is a language acceptor. So it accepts strings, and the only difference now is that it has non-determinism by its side. And so non-determinism allows the NFA to try all possible walks, right? And so if any of these walks lead to a final state, then the NFA accepts the input string. Otherwise, N rejects W, okay? And so formally what we mean by this is that the language accepted by an NFA N is the set of strings over the alphabet sigma star. Well, over the strings that can be represented by the alphabet, by symbols in the alphabet sigma, right? So this isn't the alphabet, this is a set of all strings over the alphabet. So it's a set of all strings such that there is at least one transition, right? So you'll notice that this is the extended transition function, but for an NFA. So this is the extended transition function for an NFA, okay? So this is the extended transition function for an NFA, and it says that the strings that are accepted by the NFA are all those strings for which there's at least one walk that starts at Q0 and goes to a final state. Okay, so why does this natural language description correspond to this set theoretic version? Well, that's because all this is saying is, it's saying, give me all of the states that can be reached from Q0 while reading W, right? So this is a set of states, okay? And intersect that with the set of final states, okay? So in other words, what this is saying is find whether there are any states in common between delta star and F. And so finding anything in common is signified by saying this intersection should be not equal to the empty set, okay? So that's how this natural language description corresponds to this formal, specific, and precise mathematical notation, okay? And so one last thing before I switch to an example of looking at an NFA, I'll just note that the transition function, so delta for an NFA, can essentially do three things that a DFA cannot, okay? So the first thing is that the transition function can be over-specified, okay? So what we mean by over-specified is that if you're in a state Q and you read A, then you could perhaps go to a state P, or you could also go to a state M. So over-specified just means that you can go to more than one state. Or you can have an under-specified transition, in which case, it's the example I showed before. Perhaps you have a transition for A, okay? Maybe from Q reading A, you go to P, but there is no transition for B. And finally, you can allow lambda transitions. You can allow lambda transitions, and so what that means is if you're in Q and you go to P, if you have a lambda transition, that means that you're essentially going from Q to P while still looking at the same symbol. And so this is what you could call a transition that's for free, okay? So the transition is for free because you go from Q to P without reading an additional string, okay? Without reading, or in fact, without reading a particular symbol, okay? All right, excellent. So this sort of covers the fundamentals or the basics of an NFA. We're going to look at an example next.